Question A2 discusses a special type of pendulum called the Foucault Pendulum. And essentially it was built, the first one was built in 1857, and the changing plane of oscillation, so every time it oscillates, the plane of oscillation would shift a little, and that was used to prove the rotation, the spinning of the Earth. First, we're given that the pendulum begins at a position A0 and with a velocity 0v and in the xy horizontal plane. Part A asks for the approximate equations of motion of the pendulum in the xy plane, assuming that the amplitudes of the oscillations are small. Also, we note that John is an observer looking at the pendulum from a fixed point in space, so he's not actually rotating with the Earth. That means that to John, he's just looking at a regular pendulum, and there's no fictitious forces like the centrifugal force acting on the pendulum because he's not in a rotating reference frame. It's common knowledge that for a pendulum, it undergoes simple harmonic motion in theta, which is the offset angle. The dots here means time derivative, so since there are two dots, that's the same thing as writing the second derivative of theta, or alpha, the angular acceleration. We see that r is equal to L sine theta times the unit vector. But since theta is always small, we can approximate this as just L theta. Now, since r, the vector, is directly proportional to theta, we can replace theta with r in this equation. So now we can split into components. And this is our final answer. We recall that the question actually asked for the equations of motion. Equations of motion usually refer to the differential equations that implicitly define the actual functions in time. And part B will be just writing the equations or the functions of time. And since A is just simple harmonic motion, all we have to do now is apply the initial conditions. We know that the initial position is, or the initial x-coordinate is A, and that the initial y velocity is v. And we can immediately see that the x-coordinate is given as such using the simple harmonic formula. And here we know that the speed is also simple harmonic. Vy would be and we also know that Vy is the derivative of the y coordinate, so integrating this with respect to time and using the initial condition that y0 equals 0, we can write that the y function is given as follows. So these are our two functions of time. For part C, we consider Ella, who resides at the North Pole, but is also looking at the pendulum. So she resides at the North Pole, so that means she's actually on the Earth, and she's therefore in a rotating frame of reference. What are the coordinates x tilde and y tilde as observed by Ella? Assume that at a time t equals 0, the coordinate systems of John's and Ella's overlap. Basically, the question is asking for a coordinate transformation, a rotation transformation. Let's say that this is John's frame, or both John's and Ella's frame at t equals 0, but Ella's frame is rotating at a rate capital omega. So this is Ella's frame after a time t. So we can see that the new basis vectors, or the unit normal vectors, are given by, so let's say this is x tilde caret, and this is y tilde caret. Then x tilde caret is cosine omega t and sine omega t, while the y unit vector is negative sine omega t and cosine omega t. So using this as the transformation matrix, or it's actually called a rotation matrix. And now substituting our equations for x and y from part B, we can get now part D asks us to find the speed of the pendulum, the initial speed of the pendulum observed by Ella. So since we know the coordinates x and y in Ella's frame, we could technically take a derivative of these equations and then use the Pythagorean theorem, but as you can see, that would be extremely tedious. So we could just try to use logic. So first we know that Earth rotates with an upward angular velocity, and the pendulum also starts with the initially positive v. The initial speed in the y direction would actually be v minus the speed due to the rotation, which we know is a omega, because a is the distance, the maximum distance from the origin. But we also know that the x velocity is 0. Part E asks for the initial conditions A and V in Ella's frame, such that the pendulum passes precisely through its resting position. For this part, we simply note that the origin is common throughout both the rotating frame and the stationary frame. So in order for the pendulum to return to the origin in Ella's frame, it also has to return to the origin in John's frame. And evidently the only way for the pendulum to return to the origin is if it remains in one plane of oscillation, or if the initial offset velocity is 0. So we know that the condition would be v equals 0. Part 2 asks for the condition that which Ella sees a spike at the points of maximal amplitude instead of a rounded trajectory, and there's a visualization here. And we can tell that for there to be a spike, there needs to be 0 velocity at these points, rather than the rounded trajectory, which has a sideways velocity. So in order for there to be 0 velocity at the maximal points in Ella's frame, we already know that the maximal velocity, or the velocity at the maximal amplitudes, is v minus a omega, as we found in the previous part. And we want this to equal 0. So we have V equals A omega. The next part introduces a force called the Coriolis Force, which is a fictitious force in rotating frames of reference, and it's given by 2m omega v sine theta, or more formally, negative 2m omega cross v. And our goal is to find how long it takes for the plane of oscillation to essentially reset. So as this trajectory keeps going around in a circle, we're looking at how long it takes before it returns to its original state or original plane of oscillation. So the official solutions uses a sort of shortcut solution, and we're going to be going over that first because it's a lot easier and simpler. But it might not be as satisfying because it's not a real physical analysis. It's more like guessing, not guessing, but using this equation and the boundary conditions we know. If the pendulum is located at the North Pole, then the latitude, or theta, would be 90 degrees. So at the North Pole, we know that the plane of oscillation just moves with the Earth. And you can visualize this by imagine yourself watching the pendulum from the Earth, which is rotating. And you can see that once you make a half rotation, the plane of oscillation resets. It's not a full rotation because, like, let's say my hand is the plane of oscillation, then when it's turned 180 degrees, or half a rotation, then the plane of oscillation resets. This is the same as this way. Then the time would be pi over big omega, because pi is the radians that it travels. And we also know that the Coriolis force involves the factor omega sine theta. So, and we know that sine of 90 is 1. So it's very possible that this expression is actually pi over omega sine theta, and this would be the general formula. And from there we can simply substitute 49 degrees and get a time of around 16 hours. So now we're going to go over the full physical analysis of the system, and this is going to be a lot more mathematically involved than the rest of the test, because technically you don't have to do that way, but in my opinion this method is a bit underwhelming. Okay, so on this system we have two main forces. One is the restorative force, which comes from gravity and tension, and is given by, where r is the displacement vector. We also have the Coriolis force, which is given by the cross product negative 2m big omega cross v. And we're going to want to take the components of these in the x and y directions. For gravity, and in order to take the components of the Coriolis force, we would have to look at the component of this, which is perpendicular to our coordinate x. So we would be looking at the y velocity, and then similarly for the y force, we look at the x velocity. So now we can write our equations in x and y using Newton's second law. And we actually run into a problem here, which is that these two equations aren't completely dependent on one variable. So we actually have to solve this as a system. And in order to do that, we can start by introducing the complex variable as x plus iy. So we can multiply the second equation by I and then add the two equations. So first let's get rid of m. So now we can see that this is simply z double dot, or the second derivative of z. So we can replace this with z double prime. And this is just z. But then now we have this term, which is a bit of a problem. But we can actually fix this by factoring out I, which shows y dot over I minus x dot. But we also know that 1 over I is equal to negative I. So we actually end up with negative 2I omega sine theta x dot minus I y dot. And this is actually just z dot. And now we can rearrange the terms to end up with this nasty differential equation. So this is what we call a linear homogeneous differential equation. It's linear because all of the functions and its derivatives, they appear in the first, they appear in linear terms, so they're not like squared. If this was like a squared here, then it wouldn't be a linear equation anymore. It's also homogeneous because you don't see the independent variable anywhere. You only see the function. So if there was like a t, then it wouldn't be homogeneous anymore. And there's actually a really nice way to solve these types of equations. And it would actually be to sort of guess that the solution has the form e to the I alpha t, and we're gonna plug this back in to the differential equation and then solve for alpha. And you'll see why this turns out really nicely eventually. So we know z prime is so substituting these back into here, we get and you notice how since there's an I here and an I in this term, the I actually goes away. So that's pretty nice. And you can actually see that these three terms can cancel out since, well, we know it's not 0. It can't be 0. So, yeah, it works out really nicely. And multiplying by -1, we get a quadratic equation in alpha. So now we can solve this using the quadratic formula. So now we're going to see that small omega is much greater than big omega. Well, big omega is the rotation of the Earth, and that's really slow, while small omega is the is the frequency of the pendulum, which is probably a lot faster than a day. So, and also it's squared. So to the first order, we can get rid of this term, and we can actually approximate this as so we actually have two solutions for alpha. We'll call it alpha 1 and 2. So since we have the differential equation was linear, this differential equation, we can now use a property of differential equations, which is that linear differential equations, if it has multiple solutions, the independent solutions could be added to form a more general solution. In this case, we have two solutions which are and you might be wondering what these A and B mean, and those are actually just initial conditions. There's no way to explicitly solve for them unless you have initial conditions or boundary conditions. But anyways, we have two independent solutions, so now we can actually add them to make a more general solution. And substituting our equations for alpha, we would get and now we can actually factor out the term e to the I negative omega sine theta t from both of the terms using our exponent rules. And this is our new function. So this describes, or even though this is a complex function, it describes the motion of the pendulum from a top view. You might be wondering how to analyze this even if it has the complex variable in it. We can kind of tell that this inside part, it describes the motion within the plane of oscillation. So this, because it involves the small omega. But then this part, you can tell that it has to do with the rotation of the plane itself because it has this big omega. And we know that E, the equation E to the negative I alpha t, this describes a circular motion because of Euler's identity, which is so because of this identity, we know that this term describes circular motion, and we can tell that it goes all the way around in a circle when this term is equal to 2 pi. In other words, this alpha is the rate of rotation. So we know that now we know that big omega times sine theta is the rate of rotation of the plane of oscillation. And like we said before, the plane of oscillation only needs 180 degrees to reset. So then we know that big omega sine theta t is equal to pi radians. And we finally get the same answer as before, but this time with a real physical analysis and a nice lesson on differential equations.